All right, anyways, so we learned about the alternating series error estimation theorem. But this is a lot of words. This is 5 words, and this is even longer than 2 words, which we usually abbreviate things for. So this is going to be abbreviated ASEET or ACET or something like that. So if you ever see this, they're talking about the alternating series error estimation theorem. And if you're wondering what that is, remember that's if we replace the nth partial sum, or we replace an alternating series with its nth partial sum instead, so we only sum up the first few terms, then the error is going to be less than the next term that we would have added up here. So that's what this is referring to. Now you may see it abbreviated as ASEET here. Wow, why is this quality so bad? It's all grainy. Huh, that's weird. Maybe it's because I did the poll. I don't know. Jeez, that's weird. Anyways, yeah, I don't know how to fix that immediately, so hopefully it'll get better. That didn't make too much of a difference. Oh, restart the screen share. That sounds like a good idea. Oh, worked like a charm. All right. Yeah, you always just got to restart stuff with computers. All right, but anyways, I just wanted to let you know about this abbreviation for the alternating series error estimation here. Okay, now another thing I want to talk about is probably the biggest point of confusion on this exam or whatever exam has power series in it, is knowing the difference between the first, like let's say 4 non-zero terms versus a degree for approximation or a Taylor or a Maclaurin polynomial. So sometimes the question will ask for this, sometimes the question will ask for this. Which way is it going to work right here? Or how does each one of these work? Let's take an example here. Well, how about we have the series for cosine of x? So the Maclaurin series for cosine of x is the sum from 0 to infinity of -1 to the n, x to the 2n divided by 2n factorial right here. All right, now let's see here. So what was I going to say? Yeah, so let's say we want to do the first 4 non-zero terms. First of all, non-zero does not apply to the index right here. So if it says non-zero term, it's not talking about this. It's talking about if this is going to be 0 or a power of x has 0 as a coefficient. So for example, the first 4 non-zero terms of this, if I plug in n equals 0, I just have 1, 1, and 0 factorial, which is 1. So that was from n equals 0. And remember, it's okay if this is 0. If I plug in n equals 1, I have negative x squared over 2 factorial. If I plug in n equals 2, I have positive x to the 4th over 4 factorial. And then if I write my 4th and last term here, I plug in n equals 3, and I have negative x to the 6th over 6 factorial. So when I say the first 4 non-zero terms, I don't necessarily mean go to n equals 4. And when I say non-zero, I don't mean skip this right here. I'm talking about if maybe we plugged in n for the formula and we ended up getting 0. So let's say I plugged n into this formula, I got 0. That one wouldn't count towards our total of going up to 4 here. That's what I mean by non-zero here. So this would be the first 4 non-zero terms of cosine of x. Now let's say we wanted to do a degree 4 approximation for cosine. So when I say degree 4, degree literally means the same thing that it does for polynomials. So what does degree mean for polynomials? It means the highest power of x. So that's exactly what it's going to mean here. This means that we keep writing terms, we write as many as we can until we get to x to this power. So we'd have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And now that we've reached degree 4, then we stop. So this would be a degree 4 approximation of cosine of x, which is also known as the degree 4 Maclaurin, or Taylor in general, polynomial. All right. Yeah, what if the power can't be 4? Yeah, don't worry about that. We're not going to like try to trick you or anything. It's just you just go up to whatever power of x this is going to be here. All right. Let's see. Anything else I want to say about this? Yeah, one way you may see this written, as like T4 of x. So this would stand for the 4th degree Taylor, or Maclaurin in this case, polynomial of this function. All right, so I just wanted to talk about the difference between these two because I think this ends up confusing a lot of people here. All right, and that's all I really wanted to kind of say in general. The rest is kind of just reviewing the stuff you feel like you have trouble with. So for example, if you feel like you've not really got what the parametric stuff is about, I recommend you take a look at that. But on the other hand, if you feel like you're not very good at series, or you're bad at approximating things or computing the error, I would definitely focus on that. So focus on whatever you feel the least comfortable with and just work on that here. Now, to kind of address just general issues with this class, what I'm going to do is I'm going to go through an exam here. So I'm just going to, and this exam will have all manner of questions here. So no matter what you feel the weakest in, we're going to be covering it at some point. How many questions? I think it was 17 or something, but some of them are like really small questions. So yeah, it should be, it'll definitely be doable. Anything with Euler's formula? No, I said that wasn't going to be on the exam. And then the same thing with the sum of the integers being -1/12. That won't be on there either. That was just an exposition. All right, so anyways, let's go ahead and take a look at our practice exam here.
Professor?
Yeah, what's up?
If we had something like going to the degree 4, but then our answers would be 1 minus x to the 3rd over 3 factorial, and then it would be plus x to the 5th over 5 factorial.
I said that wouldn't happen.
Okay.
Yeah, so don't worry about that. Which practice exam are we doing? We're doing the practice exam in Canvas. So if you go to assignments and then you scroll down towards near the bottom of the page, you'll see practice exam 3 down. All right, so let's go ahead and get started on this. I'll try to do as many questions as I can right here. All right, so practice exam 3. Let's do question 1. The first question is to find the IOC for the series n equals 0 to infinity of x to the n factorial. Okay, so let's figure out how we're going to do this. So usually there are 2 ways of figuring out an interval of convergence. You either look at a series that it's similar to and use that series as interval of convergence as a base, but I don't really know any series that looks anything like this. So we're probably just going to have to do this one from scratch by using the ratio test. So let's go ahead and use the ratio test here. Actually, wait a minute. Actually, I think the root test would also be pretty good for this one. I'm going to use the root test, but you could also use the ratio test here. So I'm going to use the root test for this. So remember, the root test says that we take the limit as n goes to infinity of this in an absolute value, and all that's going to be raised to the 1 over n power right here. All right, now the only thing that could be negative is the x, so I'm going to put the absolute value on that part. We have absolute value of x, and then I have an exponent raised to an exponent. So what do I do then? I multiply them together. All right. Now, is there a nicer way of writing n factorial over n? What is that going to simplify to if we just cancel out an n here? That's right. It's going to be n minus 1 factorial. So we have absolute value of x, and then we have n minus 1 factorial right here. Okay, so now let's think about this. As n goes to infinity, this power is going to get really huge, right? This power is going to get astronomical. Factorials get really big really quickly. Now, if we have an absolute value of a number between -1 and 1, then, or sorry, an absolute value between 0 and 1, like say 1/2 or 3/4 or something, if we multiply that by itself a bunch of times, what will we get from that? I like multiply a bunch of 1/2s together, a bunch of 3/4 together, a bunch of -1/2s or something. That's right, it's going to be 0. So if -1 is less than x is less than 1, then the limit here is going to equal 0 because I'm multiplying a bunch of things smaller than 1 together. All right. Now let's see here. If we're outside of this, like let's say we have 2 and that's raised to a massive power, what's going to happen then? Like if I have 2 or 3 or -5 for this, what's going to go on there? It's going to go off to infinity. That's right. So if I have like 3 to a huge power or 5 to a huge power, so if absolute value of x is bigger than 1, then my limit is going to be infinity. So I'm going to go off to infinity right here. Can we just use the geometric series test for this question? This isn't quite a geometric series. So that would just be x to the n. So this is x to the n factorial. So it's not quite a geometric series, but it uses the same kind of reasoning as that. So it's okay to think of it that way, but it's not really a geometric series. So this means that our IOC is going to be from -1 to 1, right? But there's always a catch with the interval of convergence. We always need to check our endpoints here, right? So let's see if -1 and 1 will work here. Why is it n-1 factorial? Well, n factorial is n times n-1 times n-2, 3 times 2 times 1. So if I divide this by an n, then these will cancel out. And then I just have all the numbers going down from n-1 times n-2. So this right here, all the leftovers will be n-1 factorial right here. So that's how that cancels out. All right, so let's go ahead and check the endpoints here. So let's have x equals 1. So this is the sum from n equals 0 to infinity of 1 to the n factorial. But 1 to any power, no matter how astronomically large it will get, will just be 1. But the sum of 1 will diverge by the test for divergence. And then the same thing goes for x equals -1. So if I look at -1 to the n factorial, that also will not go to 0. In fact, it'll end up going to 1. So this will diverge as well. So our IOC for this one will be -1 to 1, but then not including the endpoints right here. All right, so when in doubt, if we have a series that doesn't look like anything else, we should use either the root or ratio test to see what's going to happen. And the ratio test would have given us pretty much the same thing right here. If they ask for the IRC, would we even need to test for endpoints? That's a good point. No, you wouldn't have to do that because the radius of convergence is half the length of the interval of convergence. And whether we include -1 and 1 or not, the distance between these numbers is 2. So our radius of convergence would be 1 even before checking the endpoints. The series doesn't converge to 1. Remember, this is the sequence that we're adding up. So this is 1 plus 1 plus 1 plus 1 plus 1 forever. That's definitely not going to converge here. All right, so we got that one. That's good. Let's see here. We only have to check if it's integration. Well, if you do it from scratch from the ratio test, you need to check that as well. How do we know not to test like 2 to -2? Well, because those have an absolute value bigger than 1. So if we go back to the ratio test here, like if we had 2 to the n-1 factorial, that would go off to infinity. So that would definitively fail the ratio test here. So it's really the ones kind of on the edge here from -1 to 1 that we need to check. All right, our next question, let me scroll to that. This one wants us to find a Maclaurin series for the function f of x is cosine of x times sine of x right here. And they give us a hint for this one. We have that sine of 2x will be 2 sine of x cosine of x. All right, so this is the double angle formula for sine right here. All right, so let's see here. So if I take this hint and divide it by 2, sine of 2x over 2 is cosine of x times sine of x, which is the very function we want to find a series for. So rather than multiplying these two series together, which by the way, you can't just multiply the formulas for series together, it doesn't quite work like that. We're instead going to use the series for sine of x, substitute a 2 in it, and then divide by an extra 2. So if we look on our formula sheet, our sine of x is the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. All right, now I'm not interested in just sine of x. I want to have sine of 2x right here. So we have sine of 2x. That's just going to be me substituting in 2x for the x right here. So sum from 0 to infinity, we have -1 to the n. And then since I'm putting the 2 in here as well, it's also going to be a 2 to the 2n plus 1 x to the 2n plus 1 over 2n plus 1 factorial right here. All right, on the test, were they given a hint? Yeah, yeah, this would have been one we would give you a hint right here. All right. And then now the last step we need to do is we just need to divide by 2 here. So I'm going to divide both sides by 2. And there we go. Now we have our function. Now, one way to simplify this, so I have all of these 2's multiplied up here, but then I'm dividing by one of them. Well, that means I could just lower this power of 2 by 1. So this will be 2 to the 2n, x to the 2n plus 1 over 2n plus 1 factorial. All right, and then 2 to the 2n, an even better way of writing that would be 4 to the n. And I think that's what shows up in the answer choice. So there we go. There is our series for cosine of x times sine of x right here, using the double angle formula right here. How's the formula sheet work with honor lock? Is it digital at the top of the page? Yeah, so you'll have a picture of it like in a question box at the top of the page, but there will also be a link where you can download it and you could view it in a separate tab if you want. And don't worry, I'll give honor lock, I'll let them know that you're going to potentially use it in a separate tab, so you won't be flagged. Unfortunately, you can't just print out. What is all on the sheet? It's in the miscellaneous part of Canvas. You could look and see everything you're going to get. It's going to be the common Maclaurin series, and then the Taylor remainder estimate, and then the coefficients for Taylor series. How does the 2 to the n plus 1 change to just 2 to the n again, or 2 to the 2n? Well, I have 2 to the 2n plus 1 divided by a 2. So I divide out one of these 2's. I cancel one of these 2's like that. All right. So we got that. That's good. Next one. Let's see. Question 3. Find a power series representation for x over 1 minus x squared right here. How does 2 to the 2n go to 4 to the n? Well, remember, if we multiply exponents together, the way that works is this is 2 squared to the n. This is 2 to the 2n right here. So we have 2 squared to the n. That's the same thing as this, and then 2 squared is 4. So that's where we end up getting it. All right, so let's figure out a series for this. Now, this already looks a little bit like 1 over 1 minus x. So I bet we can modify this series to, in some way, to look like this one here. All right. So 1 over 1 minus x, that's another one we would have on our equation sheet. It's the basic geometric series. This is the sum from n equals 0 to infinity of just x to the n right here. All right, now let's see. If we ever want to square our bottom or have our 1 minus x to a higher power, what we could do is we could do the derivative of both sides of this. So if you ever have the whole bottom being raised to a power, it's best to do a derivative starting from here. So I'm going to do a derivative of this whole thing here. All right, now before I do that, I'm going to rewrite this as -1 over x minus 1. So I didn't do very much yet. I just factored out a negative from the bottom. Okay, now I'm going to do the derivative. So if I do the power rule, this x minus 1 is to the negative first power, right? So then what I'm going to do is I'm going to multiply by -1, canceling out that negative. And then I'm going to get x minus 1 squared right here. And then if we do the derivative over here, I have the sum from n equals 1 to infinity of nx to the n minus 1. Now remember, when we do a derivative of our series, we need to bump up the index by 1, because if we don't, we're going to have 0 minus 1 will be x to the -1, and then we're outside of polynomial territory here. All right, could we just square it all and then multiply it by x? No, so power series don't work that way. So we can't just like square this and then have x to the 2n as 1 over 1 minus x. Reason being is that's kind of like polynomials. Power series need to be FOILed out. So that foiling process makes squaring this more complicated than it seems. So we can't just square everything. Is that the only time the n part changes? That's right. So if you integrate, you don't need to change the index there. Can we have taken the integral of the original function? I mean, I guess so, but I think that would have been a bit harder than doing it this way here. But yeah, you're welcome to do that if you want. All right, anyways. So this right here, so we're almost there. By the way, if we're inside a square, we could flip the order of a sign, because squaring a sign doesn't do anything. Okay, so we have this, and then all we're missing is the x right here. So what I'm going to do is I'm going to multiply both sides by x. So when I do that, I have x over 1 minus x quantity squared. And then when I multiply this x, so this is x to the first, times x to the n minus 1, I add the exponents together, and I have n x to the n, like that. All right. You could do that. Yeah. So for example, let's say I had 1 over 3 minus 1 squared. This is the same as 1 over 1 minus 3 squared, because this will be 2 squared, which is 4, and this will just be -2 squared, which is also 4. So we're effectively multiplying by a -1, and it's inside the square. So it's just going to go away anyway. So yeah, you could always flip the signs of something that's inside a square. Or to any even power. What if it's cubed? No, because then the cube, -1 cubed will be negative. So it won't work for a cube. So what was the point of taking a negative sign out in the beginning? Let's see here. So it was easier to do this derivative right here. That's why we did that originally. You could also just do the derivative of this if you want right here. Yeah, you could do it without taking out the negative. It's totally fine. All right, so there we go. So we managed to find our power series for this one right here. All right. The starting index is n equals 1 because we did a derivative. Yeah, I think there's a typo in the actual online exam. I think that one started at 0. It really should be n equals 1 right here. How do we get to the last part? We just multiply both sides by x. So I did x times this, and I have the function that we want. And I have x times x to the n minus 1, and I get x to the n right here. Why can't I just take the square root of the original function? So you're saying find the series for root x over 1 minus x? Because again, we can't just square a series and just square the formula inside. Squaring a series is more complicated than just squaring the formula inside. So I don't think we could have done it that way. All right. Let's see here. So we got that. Our next one. All right, all right, so here we go. Here we get to apply what I was talking about in the beginning of class. Use the first two non-zero terms of the Maclaurin series for arctan of x to approximate arctan of 1/2. All right. Let's go ahead and take a look at this. All right, so arctan of x is something we're going to have on our equation sheet. The series for arctan of x is the sum from n equals 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus, oh, no, not a factorial, just 2n plus 1. All right. So what we want to do is we want to use the first two non-zero terms of this series. So let's write those out. So I plug 0 in for this. I have -1 to the 0 is 1. And then I have x to the 0 plus 1 is x. And then we have over just over 1. This is n equals 0. That's the first term. And then we go to n equals 1. That will give us a negative there. We're going to have x cubed over 3. Okay, and this should be a squiggly equal. So rather than adding up all of the terms in the series right here, we're instead only adding the first two. Now that's going to result in a loss of accuracy because we're missing all of the other terms that we need. But as we've seen in class, a lot of times just only using a few terms can give us a pretty good approximation. All right, so our whole goal here is to approximate arctan of 1/2, which I have no idea what number that is. So arctan of 1/2 will be approximately equal to if I plug 1/2 in for here. So I have 1/2 minus 1/2 cubed divided by 3. So this is 1/2, all right, this is an 1/8 over 3 is 24. So this ends up giving us 1/2 minus 1 over 24. And if you want to simplify this, this is 11 over 24. All right, so that is our approximation for arctan of 1/2. And then now the next question has to do with this as well. So question 5, using the A seat, or however you want to pronounce it, what is the maximum possible error for this estimate? So it's one thing to say that arctan of 1/2 is about 11 over 24, but if that approximation isn't very accurate, then it's not very useful. So we should at least have an upper bound on the error right here. All right, so how do we get an upper bound on the error for an alternating series? Well, what we do is we go to the next term that we would have included in our series. So we actually included n equals 0 and n equals 1. Let's see what happens when we put an n equals 2 into here. So the n equals 2 part of the series will give us x to the 5th over 5. Now, we didn't just have a general x, we specifically used x is 1/2 right here. So our error will be less than a sub 2, which is 1 after the one we went to, which will be 1/2 to the 5th over 5 right here. All right, so 1/2 to the 5th is 1 over 32, and 32 times 5 is 1 over 160. So this error, well, the error for this 11 over 24, it's at least 1 over 160 away from the true value of arctan of 1/2 right here. We'll be given the m value in the approximation degree on the real exam. If it's something that's not too hard to figure out, we may have you find the m, but for problems where it's not obvious what m to pick, we'll give it to you. One thing I will say is is to remember that absolute value of cosine of x and absolute value of sine of x, each of these are going to be less than or equal to 1. So if you ever see a sine or cosine involved with your m, use this approximation here. We won't tell you to do this. We'll expect you to know that cosine and sine are less than 1 here. We'll get to that in a little bit once we get to that question. All right. Let's see here. So question 6. Okay. Using the Maclaurin series for e to the x squared, approximate the integral 0 to 1/2 of e to the x squared using the first 2 non-zero terms of the series. So again, they don't say a particular degree with this one. They say use the first 2 non-zero terms here. All right. So first of all, let's get a Maclaurin series going for e to the x squared here. Let's see what that is. All right. So let's see. So our series for e to the x, this is something we'll be provided with. This is the sum from 0 to infinity of x to the n over n factorial. Okay, well then that means if I replace the x with an x squared, then I'm going to have x squared to the n over n factorial. And remember how the exponents work here. This is the same as x to the 2n over n factorial right here. Wait, why are people putting in all these signs? Did I make a mistake here or something? Okay, yeah, I'm not really sure why people are doing that. All right, anyways. So let's go ahead and use the first 2 non-zero terms of this. So e to the x squared will be approximately equal to, now we have n equals 0. We plug that in here. We have x to 0 is 1 over 0 factorial. So we just have 1. And then for our second and final term that we'll use, we plug in n equals 1 here. And we have x squared over 1 factorial. So we end up with 1 plus x squared. So what we're doing is we're saying, while they're not the same, e to the x squared is going to be kind of close to 1 plus x squared. Now, I don't know about you guys, but I certainly can't do the integral e to the x squared, at least not by any technique that I know. So what I'm going to do is I'm going to replace this with the integral of 1 plus x squared. All right, so I'm going to go ahead and integrate this. So I have x plus x cubed over 3 from 0 to 1/2. And then I just plug 1/2 in here, and I have 1/2 plus 1/2 cubed over 3. So this is 1/2 plus 1 over 24. So this is going to be my approximation for my integral right here. Okay, and then what was that?
I have a small question. If it asks for something like the first 2 non-zero terms, let's hypothetically, like if your first term was a non-zero term like 1 and your second term was 0, would you move on to the third term and then count the 2 positive non-zero terms as your terms, or would you
Yeah, no, that's absolutely right. So like, let's say in some bizarre universe, 1/1 factorial was 0 for some reason. Then we would just skip this one and then go on to n equals 2 and plug that in. So that's totally right. So e to the x squared is equal to 1 plus x squared. It's not equal to, it's approximately equal to. So while e to the x squared is not the same function as 1 plus x squared, it'll at least be pretty close, at least close to the center of the series, which is 0 right here. Do you not integrate the power series but the approximation? You could have also done this by integrating the whole power series. So this is Q6.2. Another way we could have done this problem is by saying the integral of e to the x squared is exactly equal to the integral of the whole series. And then we could have done that. So this would have been the sum from n equals 0 to infinity of x to the 2n plus 1 over n factorial times 2n plus 1. And we could have plugged these in. And these are all straight equals. These are all exact. And then at this point, then we could have used the first two non-zero terms of this. So that would have been another way to do the problem. So this would, if we use the first two non-zero terms, and then we would have our squiggly equal, this would be 1/2 plus 1/24. So another way to do it is to not use the approximation until the end right here. Okay, but we made an approximation, right? So our approximation of this integral is 1/2 plus 1/24 right here. So the next part of the question asks, using the Taylor remainder estimate, I guess we could abbreviate this one as T-ret, like that, tret, I don't know. Using the Taylor remainder estimate theorem, find an upper bound on the error for the previous problem. And I think this one was a little bit less obvious. It's a little bit harder to get the m. So in this one, we told you guys to use m equals 24, and then that this is a degree 3 approximation. Now, the m equals 24, I'm not even going to go in how we would get that. That's pretty complicated. But we could actually figure out, based on what we know, that this is a degree 3 approximation. Because if I look at the first two non-zero terms here, I had 1 to the first power, and then I had something cubed. So this cube right here, this is the highest power that I have. So this is a degree 3 approximation. So even if I didn't say this on the exam, this would actually be something you could figure out here. But I figured it was kind of non-obvious in this case, so I just wrote it. All right, so what we're going to do is we're going to use the Taylor remainder estimate here, which says that our error is less than or equal to m times absolute value of x minus a to the n plus 1 divided by n plus 1 factorial. All right, now what do all these letters mean here? Well, they told us what m is. M is 24. Then our x is the number that we plugged in for x back here. So this is 1/2. A is the center of our series. Now we used a Maclaurin series, right? So the center of our series is 0. And then n is the degree. So we have 3, and then we add 1, and we have 4. And then we also have 4 factorial down here. All right, so coincidentally, 4 factorial actually equals 24. So those will cancel out. And then 1/2 to the 4th is 1/16. So this 1/2 plus 1/24 estimate, which is 13/24, this is no more than 1/16 away from the true value of that integral. It's not as impressive as the 1/160 we got from the previous problem, but it's something. So we're not totally inaccurate here. Is n not 2 though? No, n's going to be 3 because we did the integral. So the approximation of e to the x squared was second degree, but then the approximation of the integral, since we bumped up the powers by 1, will be x cubed. Actually, you guys do get this formula. So you guys will get this. So don't worry about memorizing this. So you get this. Yeah, so don't worry about memorizing that one. We've gotten the same answer by using AC. Well, we actually can't use that for this one because this isn't an alternating series right here. So this one we're forced to use the Taylor remainder estimate. Where did the x equals 1/2 come from again? It's because it's the number we plugged in for x back here. So we evaluated our bounds here and then plugged in 1/2 for our x right there. All right. So for the non-alternating, use this. Yeah, it's the only option we have. That would be more complicated because then your answer, or so the question was, for those who might not have heard it, what would happen if our lower bound was not 0? Then we would have had the difference of 2 series, and it's a bit more complicated to figure out what's going to happen with that. So don't worry about that. How would we get m if we needed to anyway? Well, we wouldn't ask you to get m for a problem like this. It'd be kind of hard to do that here. Let's see here. Yeah, if it's if we have something with sine or cosine, like the function that we used is like, say, sine of 2x, and we needed to do like 3 derivatives of this, then we would end up getting 8 times cosine of 2x right here. So our absolute value would need to be bigger than this. So we know the cosine of anything needs to be less than 1. So this is less than or equal to the absolute value of -8, which is just going to be 8 here. So our m would be 8 for that one right here. So if you ever get a sine or cosine, you'll just do enough derivatives for that. And how many derivatives do? We do this many derivatives. So I guess for this one, it technically would have been the 4th derivative. So it should have been 16 sine of 2x. So then we have 16 sine of 2x here, but then the same reasoning applies. We know that sine is always has an absolute value less than 1. So our m would be 16 for that. All right, let's move on to number 8 here. And if we don't get to one of your questions today, like if you're wondering about something later on in the exam, we could also do stuff on Monday too. So I'll put up the same poll on Monday if you guys want to continue doing this exam or just ask random questions for Monday. All right, so let's go to 8. All right, this one's a little interesting. We're supposed to find the Taylor series for e to the x centered at a equals ln of 2 right here. Okay, so this is interesting. So we have a series that's not centered at 0, so we can't use our table of Maclaurin series to help us out here. So what we're going to have to do is we're going to have to make one of those Taylor series tables that we made before. So remember, the columns for this have n. They have the nth derivative at x. They have the nth derivative with the center plugged in, which is ln of 2. And then they have the nth derivative with the center plugged in divided by n factorial right here. All right, so let's see here. So we have n. Let's maybe do this many. Hopefully that'll be enough to see what the pattern is. So if we do no derivatives of our function, well, we're going to have e to the x. In fact, if we do any number of derivatives of our function, we're just going to have e to the x the whole time, right? Any number of derivatives that we do will just result in this e to the x here. All right, and because all of these are the same, then all of these will be the same as well. So this is e to the ln of 2, which is 2. And so this is just going to be 2 forever here. And then finally, we just do 2 over n factorial. So we have 2 over 0 factorial, 2 over 1 factorial, 2 over 2 factorial. And I think it's pretty clear what the pattern for the coefficients is going to be here. So it seems like no matter how far down we go, we're going to have 2 in the numerator, and then we're having an increasing factorial depending on n in the denominator. All right, so what does this mean for our series? So this means that our series e to the x is the sum from n equals 0 to infinity. Now our pattern was 2 over n factorial. So we have 2 over n factorial, and then we always do x minus the center, and then that's going to be raised to a power here. So this will be our Taylor series centered at natural log of 2 for e to the x right here. So it looks kind of similar to the one that we have in the formula sheet. There's an n factorial down here. This is raised to the nth, but it's a little bit different. We have a 2 here, and we're subtracting ln of 2 there. So it is a bit different. Will we get the formula for Taylor coefficients? Yeah, that's right. That'll be on there too. So we always add in the x minus a to the n. Yeah, that's right. We always tack that in at the end. Usually the hard part is figuring out the formula for the coefficients, and then we end up just sticking that there at the end. All right, do we have enough time to do this next one here? Let's see. Use the 3rd degree Maclaurin polynomial for tangent to approximate tangent of 1. Oh, well, let's give it a try. All right, so number 9. Approximate tangent of 1 using 3rd degree Maclaurin. So unlike the other problems before, this one's asking for a 3rd degree approximation, meaning we need to go up to x cubed. All right, so we're going to make what we're going to do is we're going to make a table, but we're only going to go up to n equals 3, because we only need a degree 3 approximation. Zero, 1, 2, 3. All right. So this time we're trying to approximate tangent, right? So our function is tangent. So we have tangent after we take no derivatives here. And then we're going to plug in 0 for tangent. And we have 0. And then we have 0 over 0 factorial, which is 0. All right. Oh, how do we know when to make the table? You either make the table if you're centering a series somewhere other than 0, or if you're just making a Maclaurin polynomial, like a finite degree Maclaurin or Taylor polynomial. So pretty much these 2 problems here would be the instances where we would do that. All right. So we do a derivative of tangent. We know what that is, secant squared. So we have secant squared of 0. Well, secant of 0 is 1, and 1 squared is 1. We have 1 over 1 factorial is 1. All right, let's do the derivative of secant squared. So if I use the chain rule here, I have 2 secant of x, and then I multiply by the derivative of secant, which is secant times tangent. So multiplying by another secant changes this to be secant squared, and then I have tangent here. All right, well, what's going to be disappointing is that if I plug in 0 for this, I'm going to end up getting tangent of 0, which is 0. There's going to be another 0 here. All right, and then finally, I need to do the derivative of this right here, which will require a product rule and a chain rule. So I'm going to do the derivative of 2 secant squared. So that's 4 secant squared of x, tangent of x. But then I already have another tangent here. So it's tangent squared. Then I leave the 2 secant squared alone and take the derivative of tangent, which is secant squared. All right, so that's what I get for this box right here. Now, when I plug 0 in for all of this, I have tangent of 0, so all of this part will be 0. But then I plug in 0 for these, and I have 1 and 1. So we have 1 here times 2 gives me a 2. And then I end up with 2 over 3 factorial, which is 2 over 6, which is 1/3 right here. All right, so we got to our 3rd degree, so we're done. So what does this mean? This means the tangent of x is approximately equal to 0, because we have a 0 there, plus 1 times x, because of that, plus 0 times x squared, and then plus 1/3 x cubed, which is just x plus 1/3 x cubed. So in summary, now we can just finish this. If we want to approximate tangent of 1, that will be approximately equal to 1 plus 1 cubed over 3, or 4/3 right here. So tangent of 1 is going to be pretty close to 4/3 right here. All right, I think we're definitely over time now. Yeah, 3:52. All right, so we'll come back on Monday and we could either finish this exam or go over general problems, or I think I saw a request in the chat to maybe do some of the older exams, so I could put that on the poll as well. All right, so I'll see you guys on Monday, and I hope you all have a good weekend.
Thank you, Professor.